Hi, welcome back. We are looking at continuous time Fourier series properties, so let's continue doing so in this video. All right, so I want to talk about the conjugation property first. So I was almost going to say convolution. I got convolution on the brain. Let's say x of t has Fourier series coefficients ak, right? Then it turns out that if we took the conjugate of x of t in time, the Fourier series then would be reversed, so there'd be a minus k there, and conjugated. Okay? Now, this has several consequences, particularly if x of t is real. So if x of t is real, then x of t equals its complex conjugate, right? And that implies that the AKs are conjugate even, like this. Okay, so the consequences of this then would be that the real part of AK is even to the imaginary part of AK is odd. 3, the magnitude of AK is even. And 4, the phase of AK is odd. So if I give you a homework problem or an exam problem where you're given a real x of t, then if you find the Fourier series coefficients and you plot the magnitude of them and you plot the phase, you should get an even signal, or excuse me, an even plot for the magnitude and an odd plot for the phase, for example. All right, now Parseval's relation is an interesting one, and it says the following. I'll explain this integral in a second, but just let me write it down. Okay, that's Parseval's relation. And mathematically, even before we interpret this, it's interesting because this says that an integral, and t is continuous, so this is an integral, is equal to some sort of sum. That mathematically is interesting, but let's try to interpret this equation. Well, when I take the magnitude of x of t and I square it and I integrate, then that's the energy over one period. And then if I divide by that one period, what I have is the average power in x of t. We might call that p sub t over one period. The average power over one period. Now, what is this thing on the right? Well, let's notice that, let's start with this integral. This thing that I just wrote down is the average power in the kth harmonic component of x of t. Right? And the magnitude of this kth harmonic component is exactly the magnitude of ak, because the phasor itself does not have a magnitude just of 1. So this can be written like this. Okay, and because ak does not depend on time, it can come out of the integral, and then when I integrate over an interval of t and I divide it by t, that cancels, and I'm left with this. So what Parseval's relation is saying is that the total energy in one period, or excuse me, the average power in one period of the signal is equal to the sum of the average powers in all of its harmonic components. That's amazing. This is saying that I can get the power in the signal by looking at the time-based signal, or I can calculate the power in a signal by looking at its Fourier series coefficients. Okay, moving along, we've got the differentiation property. And again, suppose that x of t has Fourier series coefficients ak. Then we might be interested in what are the Fourier series coefficients of the derivative of x of t. And it turns out that you take the original Fourier series coefficients and you multiply them by jk omega 0. Now I'm not going to prove these things. It's not a good use of our time, but I encourage you to try to prove them. And you can find the proofs online or in textbooks, but see if you can do it. And I proved the first couple in the previous video, so they have the same sort of flavor like that. But this is a very important one, okay? And we're going to use this quite a bit in the remainder of the course, so we'll come back to this one. Finally, frequency shifting says, again, if x of t has Fourier series coefficients ak, then e to the jm, where m is a constant, omega 0t x of t, has Fourier series coefficients a k minus m. That's frequency shifting. So if we want to shift the Fourier series coefficients by m, we have to multiply the time-based signal by this phasor e to the jm omega 0 t. And I do want to point out that we saw something similar in the previous video called time shifting. And time shifting was that the Fourier series coefficients of x of t minus t0 were e to the minus jk omega 0 t0 times ak. So here in the time shifting property, we shifted in time, and then that was multiplying the ak's by a phasor. Here we multiply the x by a phasor and we shift in frequency. So this is actually demonstrative of the duality property. So that is to say, you will see these sort of dual properties in effect as we look at more of these guys. So we've got the frequency shifting and the time shifting. These are dual properties. When you do one thing in time, it has a dual thing in frequency, and we observe the opposite is true. Now, those are all the properties that we're going to cover, but there are more. And what I want to do is bring your attention to some reference material. So you might find on the internet, or you might find in textbooks. This is the Signals and Systems 2nd edition textbook by Oppenheim. And I want to bring up the where are the table of contents. Series, is that going to work? No. Yeah. Okay. So I'm going to bring up the properties of these guys. Summary 3.5.8. Okay, sorry, I don't have it ready to go. Okay, but here is the table that I wanted to show you. And this is table 3.1 on page 206 of Oppenheim's textbook. But almost all textbooks will have a table that is similar to this, and you can find them online as well. But this is summarizing the properties that we've looked at. So you'll see a linearity property. And I guess before that, you'll see periodic signal, x of t, y of t, Fourier series coefficients, ak, bk. So the linearity property says that the Fourier series coefficients of ax plus by is ak plus bbk. Here's the time shifting property, right? X of t minus t0 has Fourier series coefficients ak times e to the minus jk omega 0 t0. Here's frequency shifting. and so on. I want to point out another dual property, right? Frequency shifting and time shifting were dual properties, is the multiplication and convolution. In the previous video, we saw that multiplying x of t with y of t had Fourier series coefficients that convolved. And then the dual to that is that convolution in time is multiplication in Fourier series or in frequency domain. So here's the differentiation property and so forth, and here are the symmetrical properties that we just looked at, and Parseval's relation is here. Okay, so please be familiar with these properties, and we'll use them quite a bit. Upcoming here is some examples, and then we'll get to discrete time pretty soon. See you in the next video.